Jessica Kerr, better known as Jessitron, loves software because you can almost design right into it. She believes in step 1, deploy, step 2, develop, because coding is about changing how the world works. She speaks about system thinking because there's no one like software developers for consciously growing complex systems. Find her at jessitron.com. The title of her talk, How to Get Smarter While Doing Your Job. Please welcome Jessica Kerr.
Thank you. All right, thank you all for hanging with this. It's been a long day, and I don't know about y'all, but my head is full. But sorry, I'm gonna cram a bunch more in. First I've gotta ask, how many people here have been asked in a job interview trivia questions about some programming language? Or like, okay, cool. How about like implement some trivial problem or write some SQL on a whiteboard? Some, yeah, me too. These questions test our knowledge stock, like how much we already know about a fixed topic. And yet, you pass those, you get the job, and then when you show up, do you know what to do? I sure don't, because this is like, there's a whole new code base, a whole new business domain, new processes and new people to do them with. There's a whole lot to learn before I can really accomplish anything. That's why, in our job as software developers, knowledge flow is a lot more important than knowledge stock. So this talk is about knowledge flow. It's about how do we get more learnings, how do we get smarter by doing the things we're already doing. Because we're not academic researchers, and our job isn't just to learn about the world, but our job is to learn about the world while we change it. I work at Honeycomb. There it goes. Okay, I work at Honeycomb, and on our website, we have our company values. And there's one that I really like. It's everything is an experiment. Blah, 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 blah. It's what we learn that matters. Now, that's not strictly true. No, we're not in this for learning. We're in this to build software and sell it. But what we learn makes a big difference for the future. Barry O'Reilly talked about residues earlier, which is kind of a creepy word for the future version of us, but everything we do has two outcomes. Maybe some effect on the world, and the next version of us, and the next version of our team. And this value says that we care about that. Now, I also have some puzzles about this value. I don't understand it. I'm not sure anyone at Honeycomb really does. For instance, this little Erlenmeyer flask, how does the liquid go up in a wave? Like a diagonal I could make sense of if you were spinning it, but a wave? Keep questioning, I guess. And the other one is, what does it even mean for our work to be an experiment in software development? Does it mean that every change we make, we should A/B test? No, it doesn't. That's not appropriate. In fact, through a lot of thinking about this, I've come to realize that what is appropriate for making our work more like an experiment is different at various levels of the system. So today, I want to go through these 4 levels, from a program on my computer to a distributed system running in production, to that system and its users, to that system and the team that develops it, and talk about ways that we can make our work not strictly an experiment, but more experimenty, so that we can learn more from what we're already doing. Spoiler, the takeaway is everything is an experiment if we look at the results. I majored in physics in college, which I love, because my biggest takeaway from my physics major, besides that that physics was unsatisfying once we got to quantum because it wasn't deterministic and software was and much better. My biggest takeaway was this process of systematic testing and measurement that we did in physics lab. So you write in your lab notebook, you describe the experimental setup, and then, here we're gonna like roll a ball down a ramp, and then it's gonna bang, hit a block, and we're gonna time that, and we're gonna measure the acceleration of gravity at like a couple different angles to see if the acceleration of gravity is a constant. And so we do that a couple times, and we write in our lab notebook, there it is, the results, and then we analyze the results and we compare those to what we expected, and then we get an A. So the structure here is first we state our expectations. What do we expect to happen? And here there's a theoretical, so this is like the calculations of what we expect the acceleration to be, and that comes from a theory. Here the theory is provided by teacher. And then we take one action. In this case, that's rolling the ball down a ramp when varying the angle of the ramp. And then we look at the results. And here we have compared the results with the theory, 55% error. And the purpose of looking at the results is to update our theory. Because the whole point of an experiment is to either invalidate or not invalidate some theory of how we think the world works. Now, we don't actually do that in the physics experiment because this one is a toy and we're just happy that we got consistently 55% error. Okay. But this technique of systematic testing and measurement, I find very useful in software. Just the routine of it. For instance, last week I gave this talk at a Swift conference, and so I figured, I'll learn a little bit of Swift. So I went to the documentation. Here I'm going to be provided with some theory about how the language works, and it tells me how to print. Great. And then the very next thing is how to declare a variable or a constant with var and let. And I'm like, ooh, I know how var and let work from JavaScript. But I don't, so I have some assumptions, and I'm like, well, there's how I think var and let should work, there's how I know they do work in JavaScript, where is Swift in this? And this is where I come to experiments. So, all right, I've got a mutable array and an immutable array, and I expect to be able to set the mutable array to something completely different, and it lets me do that. I don't expect that to work here, and indeed, it gives me an error. Cannot assign to value. Good, good. All right, but what about mutating methods? Because there's an append method here. So I expect to be able to mutate the mutable array, craft conf, I can. Is it going to let me call append on the constant? And no, it does not. So even though these are the same type, they're both arrays, Swift is smarter and is not going to let me mutate the immutable array. But also knowing JavaScript, what if I make a supposedly immutable array and it contains the mutable array? Then I'm going to have craft conf in there, right? But what happens if I append something else to my mutable array? So that's an array of 3 elements now. But what is in supposedly immutable? Aha! It is not 3 elements. It is still craft conf. And from this I can deduce that Swift has made a copy of the mutable array at the point where I declared the immutable one. All right, that's different. And here's the thing. Every one of us works in a different world. It's not like physics, where I can ignore my 55% error and not update my model because thousands of people before me with more rigorous experimental setups have measured the acceleration of gravity and I believe them. In software, we all work in our own world. There's different languages, every version of that language different sets of libraries and versions of those libraries and build systems and what computer did you build it on and what was in your node modules at the time. And then there's our code bases. The things that we each type don't all do the same things because we're not in exactly the same world. And that's why we get to science all the time. We get to do tiny experiments to find out if our world works the way we think it does right now. Because everyone's model of any given software system is incomplete and out of date, and everyone's model is incomplete and out of date in different ways. And the beauty of software is that we can ask. In a program on our computer, we can just run the thing and see who's right. Very satisfying. Okay. So here, we've done some stating expectations and the other things. Ah, man! This is why I don't trust their... No. Okay, we'll see how long that lasts. Please yell or raise your hands or something when it goes out again. It's been doing that in here today. Okay, another thing that's great. The state our expectations step. There's nothing like so blatantly state your expectations as test-driven development, where you write some unit tests that describe what you want the software to do. Don't read these, they're just unit tests. And then it fails, but you expected that because you wrote the test first. And then, unlike in physics where you have to adjust your expectations, no, we go change the world. We go change how that software works until the test passes. And that, I just love that about working in software. We really are, we're all in different worlds, but we get to make ours work differently every day. And then we change the world of all of our users when we get it right. Until, of course, you think the test is going to pass and it doesn't. And then you're like, okay, look at the results. What happened here? And then I get to learn over and over and over again. Read the error message. Look at the results. No, the whole error message, Jess. And sometimes when that's still not enough, I'll go in and I'll add some clues for myself in the form of a console.log or a printf or whatever. And here's the thing. That little log statement that I added for myself is a scientific instrument. In the history of science, there's big movements and discoveries when our instruments advance. So the microscope made possible the discovery of cells, and then better microscopes made germ theory obvious eventually. And when we have particle accelerations, then we can study what really happens inside an atom. Particle accelerators. So science advances with scientific instruments, and as software developers, we have complete power to insert whatever scientific instrument we want right into the system we're studying. Biologists go through an amazing amount of trouble to insert bioluminescent marker genes into the corn that they're trying to change, and then they can't sell it with that gene in there, and it's a huge pain. We can delete this printf whenever we want. We have this power to get inside the system and make it tell us what's happening. So our work is more experimenty if we create our own scientific instruments whenever we need them. Or we could get really clever and open the debugger. Because the debugger is like all of the printfs that I could need right there in front of me, and I can step by step through the code, and that's incredible. It really gives us, like a microscope, strong visibility into what we're doing. So at this level of running a program on your own computer, the debugger is the most versatile scientific instrument. I still use console.log mostly, but I should use the debugger, but let me know if you can actually get that running in VS Code. Okay, but there's another piece of the systematic testing and measurement that I haven't added yet, and that is this picture. We're describing the experimental setup because we each work in different worlds in software, and for this experiment to be useful to anyone else, I need to know which world did it work in. So we have a Docker file. And then we put the Docker files into a Helm chart. We put the Helm chart into the Terraform and blah, 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 blah. We put a lot of work into describing the situation under which this experiment yielded the results we expect. And that's very helpful. And it gets even more helpful as we want our work to be reproducible. But once we get out of our computer and into production, it's never going to be perfectly reproducible. Because there's network, and there's things failing, and there's other software upgrading, and maybe there's an LLM component in here, and who knows what the users are doing. And we no longer have perfect reproducibility. And at a program level, you can reason about your code, but in the distributed system, where you're crossing process boundaries, that reasoning is not guaranteed to be correct. So we have to do something else. We need a different paradigm of experimentation. We need to, yes, test on your computer. Yes, test in CI in a defined environment, in a container. Also test in production, please. Your customers are testing in production. Are you looking at the results? So we need to measure and adjust after every deploy. Here's a fun example of that. A few months ago at Honeycomb, Martin Holman was trying to do something or other with the session database. I forget what he was actually trying to do, but before he did it, he took a look at how's the session database doing, and this is the free space on the Amazon RDS instance for our session DB, and it's at 15 gigs at the beginning of the period, and then a month later it's a little over 10 and going down, and at this rate, in 3 months, our session database will have crashed. Well, that's bad. That's not expected behavior. So we noticed this and decided to investigate. So he's like, okay, where are we putting stuff in the session database? So he does a query. This is in Honeycomb. And he looks for wherever there's a db.duck query that contains sessions. So this is a scientific instrument. The telemetry data, which is data emitted by an application for the purposes of developers and operators knowing what's going on. Every piece of telemetry data is a scientific instrument, and every attribute on there is one. And this gives us the visibility to say, okay, there's a lot of selects, but there's also 6 million inserts over whatever time period this is. Who's doing that? Okay, so drill into just the inserts, and here there's about 20,000 of them almost. The granularity is 1 hour, so 20,000 inserts an hour. We do not have 20,000 logged in users in a given hour. More like 2,000. So what's going on here? Why do we have so many? Click into that and look at a distributed trace, and it's saying that there's no user in the session. Why do we have a session entry for no user in session? Well, the answer is here. It's in this push redirect URL. Whenever someone lands in ui.honeycomb.io, we're going to send them to the login page, but we've got to store where they landed, so if they actually log in, which these bots are not, then we know where to send them. But the redirect URL is /. That's the default anyway. What if we didn't send those? How many are /? We can do a count by the redirect URL, and 5.99 out of that 6 million are actually going to the default place that it would go anyway. So Martin's like, okay, before I do anything else in the session DB, I gotta fix this. And he changed it to not save a session DB record whenever they just hit the default URL. And you can tell when he did the deploy. This is the count of inserts again. And there's a plummet. And then he can check, okay, now what is the redirect URL? And they're all interesting. And you can see that nice purple line there, that's someone violating our terms of service by scraping our website. But we can tell who. I don't know what that big spike is, but at least these are more interesting. And then he can go back and he can look at the graph he looked at in the first place, and now it is different. We have more free space that shoots up over there, and more importantly, the line is now horizontal. So the free space is not going down, and we're not going to crash for that reason for years and years. All right, so that was an example of looking at the results, and especially the ones you didn't expect. He didn't go looking at the free space expecting to find anything interesting at all, but he did. And when you see something you didn't expect, like, what's his name, who was growing some bacteria and noticed that some of them didn't grow and paid attention to that and found penicillin. The ones you didn't expect are the best for updating our theory, because our model of our software is always incomplete and out of date, and this is how we get clues about where. One other thing, and observability here becomes your most versatile instrument for your production systems. And one other piece, at the beginning, Martin started from an observation. In his case, it wasn't even like one he went looking for, he just noticed. And even more than an observation, we also start with an intention, because we're not just learning about the world, we're learning about the world in order to change the world. So in this case, Martin had an intention of keeping the session database from crashing by changing the slope of that graph. And if you can identify that, then your experiment of whatever you're doing has more rigor. Okay, but then please consider the production system and users. And if we think the production system is unpredictable, well, we can't even pretend we know what our users are going to do. And in changing our system, the purpose of the changes that we're deliberately making is to affect how the users work, and are we giving them more value, and are they using Honeycomb more? Are they spreading it to their colleagues? We want to change that. But yet, we have no way of creating controlled conditions to test that change. So in this case, we need to check the effects of what we do, and the gold standard for science at this level comes from medicine. It's the randomized control trial, where you divide people into two groups and you do a study, and is there a variation in the effect you're looking for, and also did more people die or get cancer or whatever. This is a study that, like, my doctor read 15 years ago now, before he recommended this particular kind of birth control. And they did a study, and in the study, nobody got pregnant, and there were no noticed side effects, and everyone was happy. And so I got that procedure. It's cool. But in software, what does this look like? Here's a highly technical example, and this one's fun. At Honeycomb, we run a lot of AWS Lambda, like a lot, because when you do a query in Honeycomb, our database says, oh wow, you queried over 30 days, that's a lot of data. I need this to be fast, and it spins up Lambdas to run over all the data that's in S3, so we use Lambda as compute on demand for running queries, which is unpredictable and costs us a lot. So a couple years ago, AWS came out with a new Graviton processor, an ARM-based processor for Lambdas that was going to be faster and cheaper. And we were like, oh, yeah. And faster is also cheaper with Lambdas because you're paying by the microsecond. So we were all over that. So Liz Fong-Jones promptly spun some up. She changed it so that half of our Lambdas are running on ARM and half on the old AMD processors, and we're able to compare that with our observability. And the result is the P99, so the slowest of the new Lambdas are a lot slower, and the median of the new Lambdas are also slower, enough that it cancels out any cost saving, so it's not cheaper and it's not faster, and it is more unpredictable in its speed, so meh. So Liz updated the feature flag so that we're running just 1% on the new processor, make sure it doesn't break, and 99% on the old. Oh, and feature flags. Feature flags are a scientific instrument. Totally let us run experiment. So another thing that Liz did was, in addition to updating her theory that hopefully this was going to be cheaper and faster, she's willing to back up and try again. in our work, this is like the core of what honeycomb means by this experiment value. Be willing to say, well, that didn't work, let's try something else. And that makes it so much more of an experiment. Everything we try is not a commitment, except to learn from it. Now, Liz backed up, but then she went and looked at why was it so much slower. And some of it was just AWS didn't have as many of these new processors, couldn't spin them up as fast. Some of those slow ones are just waiting. And the other one was we're on Go 117 at the time, and there was some optimization missing. And then the compression library we used, which is super important, was also not optimized for the new processors. So Liz put in a pull request to the library in Golang, and we updated to the new version of Go a little ahead of time. And AWS fixed its capacity constraints. We didn't have to do anything about that one, except wait a little while. And then it got better. And this is today, or recently anyway. We're now running 99% on the new processor. It's about the same speed, and it is cheaper. Relative cost goes down, win. So this took some time. There were a few months in between there. But the trick is just because something doesn't work right now in the system you're in right now doesn't mean it never will. And it doesn't mean that it doesn't work for other teams. So stop saying that pairing is terrible just because you hate it. Or maybe you hate it in this team with these people. Try and try again, try everything twice. In this case, if you can describe the situation in which it didn't work, that's useful information, and then you can consider trying it again in a different situation with a different team, maybe. Okay, now one more, and this one actually involves users. So here's a real A/B test. The navbar reorder. This is the growth team. Their task is to help new users to Honeycomb get some value. And the way that happens, step 1, make an account. Step 2, send us some data. Step 3, step 4, clues. So we want them to get clues about how their software is running in production to get some insight. At Honeycomb, we talk about the mean time to WTF, which is how soon you go. That's not how it works. Oh yeah, that is how it works. It's telling you that's how it works. But what do they need to do in order to get those clues? And the growth team said, well, they really need to run a query. They need to run a query over their own data, and that'll give them some idea of the value of Honeycomb. So they started from observations of the people who log into Honeycomb. What do? And they looked at amplitude, not this chart, but a similar one. Amplitude tracks like people's flow through the product. And they learned that a lot of people who never got to run a query landed at this screen. Settings. This is completely useless to them. They do not need this. This is for advanced users, and it's totally not helping them. Why did they get here? Well, maybe because on the navigation bar, this is like number 2 right after new query, and it's called data sets, which sounds like tables, which sounds like go here to look at your data. Right, so the growth team was like, okay, here's something to try. What if we called that data settings, and we moved it way down to the bottom, and we moved more useful things up, and while we're at it, put history at the bottom because you don't have any yet. And rename new query to query because that's supposed to be less scary. All right, so they needed to try this to find out whether this helped. And conveniently at Honeycomb, we have these free accounts. Like our free tier is like forever and is like 20 million events per month. Plenty of small companies subsist on that. So we've got these new users that are starting every month, and none of them have a sales rep saying, don't experiment on my customers. So they're fair game. So for a month or two, they divided the new customers into 2 with the feature flag, and half of them saw the new nav bar, and half of them saw the old nav bar. And then we can look at the results. And sure enough, way fewer of the new nav bar account creators went to the data settings page. That's good. That fits our theory. More people clicked on good things like triggers and service map and SLOs. Did they run more queries? Well, Yes, but based on the number of people involved in this experiment and the difference here, which isn't super large, we can't say that this is statistically significant. There's a greater than 1 in 20 chance that this was random. But it's not any worse. So the green team brought these numbers to the rest of Honeycomb in demo day and showed it to all of us, and everybody was super impressed and like, wow, that's so much better. Oh, feature flags, by the way, are the most versatile instrument at this level of the system. And we can use this to update our theory. But here's the thing. On the green team, you look at that like data sets that goes to a settings page. And you're like, well, maybe if we name it right and move it down where it belongs, it'll work better. Duh. Indeed, our researcher, Justin at Honeycomb, he tells me that a lot of these, like where you do like user interviews and A/B tests in the product, once in a while, you actually are curious and don't know what the result's going to be, but usually you know what the result's going to be, but you need to prove it to somebody else. So every navbar item has a team behind it, and nobody wants their navbar item moved down until you show them these numbers. And then they believe you, and nobody's going to try to contradict these numbers with excuses. No, everyone was super friendly. So in this case, the theory that was updated was really the wider sociotechnical system. It was the whole team and organization that maintains this software. Our collective models were brought into a more consistent state and at the relevant point. So sometimes it's not your theory that you're updating. And when we want to work with this level of the system, with the software and the teams, this is something different. It's not like completely unknown like the users are. We don't know who they are and what they're doing and whether they're actually pen testers. We know these people, but the thing is, these people as individuals, well, they're individuals. They're not generic people, and we can't run randomized controlled trials at this level. What we have here is a semathecy, a learning system made of learning parts. This is a word coined by Nora Bateson, anthropologist, from the Latin sim together and mathesy learning, to distinguish it from a system that you might have any hope of mechanically understanding, because a semathecy is always changing. And I like to put the running software inside the semathecy with the developers, because the code is learning from us because we change it. And we learn from the code, from the error messages, which we always read, and the observability data that it sends us, the data that it updates in production, the tests that fail, we're learning from that. So I include the running code as part of the flows of learning here, and also all of our tools. It takes our IDEs and our deployment systems to get that into production, and it takes whatever query interface and SQL prompts that we get data out. So our code, our tools, and the people on the team form a semathecy. And this is a learning system constantly changing because we're always learning. And can we use randomized control trials on this? No. All right, so now we're talking about a social world, sociotechnical really, because it includes software. And I love this article, Cause, Effect, and the Structure of the Social World, by Megan Stevenson, whose PhD is in statistical methods for this sort of thing. And she's in criminal justice, actually, and she's reviewing 50 years of randomized controlled trials. And she says in the abstract rather nicely, social change is hard to engineer. When we're trying to change a system that includes people, there's all these stabilizing forces. If you want to go out and try this new technology, the rest of your team is going to be like, no, I don't want to learn that. Get back in TypeScript. There's stabilizing forces. And also, even when you make a positive change, you know, the wider system wins. So, the iron law of evaluation says that the expected impact of any experiment in a wide sociotechnical social system is 0. and this isn't even Stevenson's law. She just cites this from 20 years ago. We have known for decades that randomized controlled trials in political systems and criminal justice, they don't work. A jobs program that worked over here doesn't work over there. Or if you follow the people for long enough, they're eventually dragged back into poverty. And yet we keep doing it because that's how academia works, and it does get you published, and it does get you promoted, and it gets you tenure. That's a different problem. But what we can learn from it is don't try to use randomized controlled trials inside your teams. Talk to people. What does work, and that medical study, by the way, like 12 years later, they did another one because actually there were a bunch of side effects and allergic reactions, and a bunch of people had to have surgery to get the thing removed. Mine's fine, I'm good. But that brings up the point, keep looking at the results. And it's when, in the criminal justice example, it's when people went back and looked at the long-term effects of the study that they couldn't see anything. Or when they tried to reproduce it somewhere else, they couldn't see anything because every social situation is different. And you can't just replicate a procedure from one to the other. And that applies in our teams too. The correct paradigm here is called action research. And this has been around since the 50s, and it's getting better known. The thing I love about action research is that this meta-methodology, recognizes that we are going to change the systems that we're studying. When you're in a social system, you're changing what you're looking at. And that's okay, because actually the whole point of studying it is in order to change it, so let's just admit that we do these things together. A fun part about action research that makes it really practical is that it's really a spectrum. I mean, as a practitioner, we tend to focus on acting, but we typically do some planning. Hopefully we notice some things before that, and hopefully we look at the results. And the action research is more excited about the reflection and the observing parts, and the acting is kind of a detail, but it's a spectrum, and so we can work anywhere along these spectrums, depending on how experimenty we want our work to be, or how sure we are that we know what to do, or how low risk. Now, this is a little different from the other paradigms. Yes, we're going to start from some observations, hopefully, but we can't describe the whole situation. It's more a matter of listening. And it's not so much about stating our expectations, those are our assumptions, yes, state those, but our goal becomes to form new questions. Because in the days of ChatGPT, answers are everywhere. Answers are cheap. It's the questions that have power. And then maybe we take an action, or sometimes the questions are enough. Doc Norton points out that as a manager, what you ask about is more powerful than what you tell people to do. If you tell people to write secure code and always have full unit tests, but all you ever ask about is when is it going to be done, you're not going to get secure code. You shouldn't get secure code because you're asking about something else. With a colleague, you could maybe wonder, so why did you prioritize this? Or more politely, how did you know that this was the most important thing to do right now? And you might find that suddenly they're doing something else. So maybe take an action. And then look at the results. All the results that you can see. Keep looking, not just the immediate ones, and not just numbers. Numbers are fun when you can have them, and they're really useful for changing other people's minds. But more useful to us in updating our theory about how our teams work and connect is really the more qualitative answers we get from asking good questions and new questions and really listening to the answers. And then we can update our theory continuously. We know we're always wrong, but we're always trying to get better. And there's no backing up. There's no backing up in a social system. We're always the next version of ourselves, and that's okay. If nothing else, we experience something together when we try a new thing on our team. But be willing to move on and try again, and that's what makes an experiment. Here's an example of that. Now, when I try something new with my team, there's various degrees of experimentiness, and in this example, I'm going to describe maximum rigor of experimentiness. So Avdi is my partner, and he was hired to help a team be more productive. And he noticed that this team, there's 3 developers. One of them wrote the software initially over the last 10 years, and he can get things done if he could just focus. And he knows where everything is, and he can make changes, and he has permissions for everything, and he can log into New Relic. And then there's the newer people on the team, and they've been around for close to a year. They're not brand new, but still, this system is changing faster than they can get a handle on it. And they are more junior, but they're trying, and they're smart people. So Avdi has a theory that that all the knowledge in this team is in the purple developer. So he's going to try something. First, he starts with the observation that most of the team is not able to make progress. Everyone's always waiting on purple developer. And then he has a theory of what's going on, which is all the knowledge in the system is in purple developers' heads. And then once you make your theory explicit, you can often find ways of testing it that are faster than actually doing anything by asking some questions. For instance, Avdi can pull an item off the backlog and go to blue and green and say, how would you do this? What do you think is involved? And they're like, gosh, I know that's going to require changes over here, but I don't know how to test that, and I don't know what else it would affect. So it's kind of scary. And then you take that same ticket, and you go to purple developer, and he's like, you just change over here. I mean, that's going to break this over here, but I'll just change that too. It'll be fine. And you notice the delta in confidence levels, and you're like, yeah, okay. I think there is a knowledge differential there. So you can often test stuff with just questions. By asking, if this is true, what else would I expect? That's how you find tiny little experiments that are super quick. And then there's what do you think we can do about it? In this case, Avdi decided to try ensemble programming. Get the team together to all work on one thing at the same time. One person is at the keyboard, and it rotates who that is. But the trick is that the person at the keyboard isn't allowed to make any decisions. They have to take instructions from the rest of the team. That way, every decision is voiced. Everyone gets the chance to ask, how did you know to do that? And what else is this going to affect? And why did you even look there? Wow. And everyone learns everyone's keyboard shortcuts, too. And then you can ask, why do you think that will work? Now, in this case, Avdi's proposal was we try this for a couple hours. It would be totally fine to say, why do you think that will work? I don't know. Llewellyn talked about it and it sounded cool. But in this case, he actually does have an idea, which is that ensemble programming it totally maximizes knowledge flow within the team among the people. And it brings everyone's knowledge to bear on the most important thing to be doing right now and spreads that knowledge. Okay, so he has a reason. And finally, what are you going to look for to know whether it worked? If it's working, he expects to hear things like, oh, that's how you do that. Now I know, thanks. And oh, hey, can you give me a login to that? If it isn't, if one person is talking the whole time, forget it. Let's not do this again. And then what else should we keep an eye on? Let's make sure productivity doesn't drop even further and that nobody's miserable. And by the way, in this case, it actually worked weirdly well. Everyone loved it, and they did ensemble programming for months. They did it like almost every day. And then they kind of got bored with it and moved on, and that's okay too. Experiments don't need to work forever in order to work. So this was a big success. But a trick is, and this, in my opinion, is the only important part of Agile, the retrospective, a structured time to look back and say, what are we doing? Is it working? What's not working? Can we fix it? What's working well? Can we amplify it? if you're doing that, everything else can be derived. Oh, and when I'm not being rigorous, I just ask, what's the worst that can happen? Because the worst that can happen in a couple hours is we learn something, and we become a little smarter. All right, so, and when we become smarter, from looking at the results, the experiment changes us, because in a symathesy, it's always about the next version of ourselves. Are we better able to work together? Oh, and the most useful bit here, the most versatile instrument is relationships, so that you can ask all those questions. Okay. These are the 4 levels, and we've talked about the most versatile instruments. Now, at all levels, if I were a CTO, my next question is definitely, okay, how do we scale it up? And my answer is, you don't. Experiments are about being small. They're about small changes that work in the system. They're not about changing the wider system. If you want to change the wider system, this is my recommendation. There's all these frameworks for scaling Agile, and they're all crap. Beth happens to be the child of Kent Beck, but Beth is smarter. He'll tell you that too. And Z has the only hope I've ever seen, and this is the radical culture of culture building is about building reproducible structures, reproducible biologically, not by copying. You can't copy best practices. You have to copy the process, the questions, not the answers. But Beth has pointers for how to build a fabric of norms and alignment instead of rules and standards. And it's really good. This is not a free video. This is a link to, please give Beth $10. Z deserves it. But she put it up. Z put it up because I asked them to. That is the best hope for changing our wider system, not just a team at a time, but the whole way our organization builds higher quality software. The other way that we can scale it up is by sharing our experiments and their results with each other. So if you do all these things and then you bring it to the wider community, it could be a blog, at conferences like this, and I don't mean just on stage, I mean talking to each other. If we compare the results, then we're doing science. Because science is not something an individual can do, it's something a culture does. And we, as an industry, are also a symathesy. And we can learn how to do software better because we do not know how to do software right. We are still figuring this out. And we can figure it out together if we're varying degrees of experimenting and varying success at sharing that with each other. We're going to get better. The most important thing is that everything is an experiment if we look at the results, because if we really look at them, they will change us. We are people. We are not a fixed model, and we will learn. So our organization is a symathesy, and my conscious participation in it makes me a symathesist. And sometimes I record my learnings in code. There's resources for this talk here. Everything is an experiment if we look at the results. Thank you.